Greetings everyone. I am Uday Sharma from the EEE Department of Institute of Aeronautical Engineering. Today I am going to discuss about the topic power semiconductor devices and components for new power converter developments. Let us discuss what is a power semiconductor device. A power semiconductor device is a semiconductor device used as a switch or rectifier in power electronics. The devices like diodes, thyristors, semiconductor rectifiers or SCRs, MOSFETs or metal oxide semiconductor, field effective transistors or a type of transistors, triacs, BJTs, etc. are called as semiconductor devices. We can see the power semiconductor devices are classified into two-terminal devices and three-terminal devices. Coming to the two-terminal devices, PN junction, PN diode, Schottky diode, power MOS these two are the two-terminal devices. Power MOSFETs, JFETs, IGBT, BJTs, and thyristors are three-terminal. They have the terminal called gate. Power electronic converters plays the key role of taking electrical energy from the power system and turning it into a suitable form needed. The power electronic devices, the types are diode rectifiers, AC to DC converter, or we can call control rectifier, DC to DC converter, DC chopper, AC to AC converter, or AC voltage regulator, or DC to AC converter, we can call it as inverter. The main use of these power converters is using stable or standard signal and converting it into variable signal. Suppose if we take a DC chopper, it gives a DC stable input and gives the output of DC variable DC output. Trends in power electronic converters. WBG technologies or wide band gap technologies. Silicon carbide or Schottky barrier diodes are becoming the device of choice for the systems between 300 volts to 1200 volts, which require anti-parallel diodes. Lateral high electron mobility transistor or gallium nitride devices from power electronic systems under 650 volts have also reached the market and are finding commercial applications in which efficiency and fast switching are design requirements. Like the gallium nitride devices from power electronic, these are used for fast switching applications. Current and midterm research efforts should produce developments related to bidirectional 600 volt gallium nitride MOSFETs or 10 kilovolts silicon carbide bidirectional insulated gate bipolar transistors or IGBTs. Silicon carbide MOSFETs and IGBTs rated about 10 kilovolts and more gallium nitride based power applications specific integrated circuits incorporating optoelectronics. The main issues that should be addressed are those reliability concerns that hinder greater adoption of silicon carbide and gallium nitride devices. Examples like reliability of the silicon carbide gate oxide, material quality for moving the larger wafers, which should bring needed cost reduction in addition to potential cost savings at the system level. Power cap packages capable of removing large heat fluxes from the small area devices. Devices based on gallium arsenide and gallium nitride on native substrate do not seem to be viable at the present time, as they require more basic research. As we can see here, the silicon carbide are high power and used in wind turbines, railways, inverters for industries, power conditioners, electrical vehicles, and hybrid electrical vehicles. And this is high-speed one or gallium nitride high-speed switching used in the PCs, data centers, servers, or AC to DCs. Here we can see the operating frequency is 10 millihertz. 10 10 megahertz. As we know that time is equals to 1 by frequency, the frequency becomes 1 by time. If frequency increases, the switching time decreases. That is, it's fastest to switch. As frequency decreases, the switching time increases. So the silicon carbide are low switching with a higher power. They can withstand the higher power. The gallium nitrides are having the fastest switching frequencies. As you can see here, silicon carbide are higher power voltages less than greater than 1 kilovolt with higher current in the niche market. The gallium nitride on silicon for higher frequencies and mid-range voltages, less than 1 kilovolts up to 100 amperes. This is for the mass market. Let us discuss the other trend in the power electronics. That is the silicon technologies. Silicon devices continue to be the devices of choice for those applications in which high switching frequencies, high temperature operation, and the very high efficiencies do not override the requirements. But cost is at most important. Like the high switching frequencies and the high temperature do not vary the output of the requirements or do not vary the requirements of the system, but the cost which we want to the operation should be done in is the most important one. Then the silicon devices are the choice of this market people. Silicon superjunction MOSFETs continue to improve. For example, the specific on resistance is currently 1 ohm per millimeter square, but still far from the limit of 0.1 ohm per millimeter square for 600 to 650 volt devices. These devices may be more expensive for voltages above 900. Silicon IGBTs are also improving. They also improving in performance by working on the plasma profile, particularly near the emitters. And the new developments on trench-based IGBTs continue to extend the second limit while providing cost-effective solutions for higher current applications. And the research focuses in higher operating junction temperatures for IGBTs. Currently at 175 degrees Celsius, which is enabled by copper bonding and the diffusion assembly of chips, the target temperature of the operation 200 degrees Celsius. As we know, in any appliances, increasing the temperature, the switching or the working of the components reduces. Even it may be the 1 degree Celsius, the efficiency of the system varies. Currently, the silicon-based IGBTs have a working temperature of 175 degrees Celsius. And the research is being done to increase the working temperature of these IGBTs to 200 degrees Celsius so that they can work at this temperature too. Nanotechnology will enable the increase of operating voltages of the silicon in silicon carbide or gallium nitride devices by reducing their on-state resistances. As example, nano IGBT would increase its current capability by giving a factor of 3, and nano cool MOS have a reduction of 5 in its on-state resistance. Like if you take the nanotechnology, they have a vast difference from the general compared to the general technology. They have reduction in the on-state resistance. They have the capability of increasing the current, etc. And the few more trends in the power electronics is a passive component technologies. The main technical issue with the designing magnetic structures for high frequency operations, including fringes, fluxes around air gaps, minimization of the leakage inductance, packing, and thermal management are three-dimensional printing. These passive component technologies revolve around this three-dimensional print. Let us see it as a part of this electronic packaging and integration. Heterogeneous integration of passives, the wide band gap technology semiconductors, integrated circuitry of drive, control, protection, communication, and advanced thermal management devices and methods is a major challenge. There are several products integrating semiconductor devices and passive PCB substrate, leading to concepts like the power system in package and transfer molding technologies. These technologies must ensure manufacturing in terms of materials, processing, reliability, and thermal management constraints, which limit potential size reductions. So I want to conclude this topic here by concluding the what are the topics and trends in the power semiconductor devices. Thank you. This is Uday Sharma signing off.